continuation of working stress method. I shall continue today's lecture also on working stress method. So, our today's topic, I shall continue the lecture number 5, that is working stress method. Let me just briefly tell that assumptions. Yesterday I told the assumptions. So, let me just enlist it related to that working stress method. At any cross section, plane sections before bending remain plane after bending. So, that means actually your strain, the strain will be linear. That assumption, this assumption will be valid only when the strain is linear. All tensile stresses are taken up by reinforcement and none by concrete, except as otherwise specified. In a special case, because concrete can take little bit of say 10% approximately, you can say the tensile stress. So, in exceptional case we can consider that okay, concrete also will take tension. So, our next assumption that in our case we shall not consider that concrete will take tension, everything will be taken care of by steel only. The stress strain relationship of steel and concrete under working loads is a straight line. So, this is also another assumption, and that these are all assumptions I am talking from IS 456 2000. And the modular ratio M has the value 280 by 3 sigma CBC. Sigma CBC permissible bending stress in compression. Sigma CBC, that concrete bending stress in compression. So, these are the 4 assumptions, and you can get it in IS 456 also. I am not going to detail of this because I have already listed this table, already I have given this table in the last lecture. So, just to make it in a complete form that I have just written, and you will get it in IS 456 also. And I have given only those 4 generally we use it. Most of the cases we shall use M20 and M25. Permissible stresses in concrete, and again we have given 4, M15, M20, M25 and 30, and bending compression and direct compression and bond average plane bursts in tension. So, whatever it is, if it is in compression or if it is say your high yield strength deformed bar, then we have to make some kind of multiplication factor and then we can get that required value. That is the standard procedure we do in our calculation. So, we start with one value and then we can multiply with certain factor and then we can get the required value. That I shall tell you in due course when we shall come across those type of problems. And permissible stresses in steel reinforcement, this one also, this table also I have given, and here you will find out that difference particularly for Fe 250 mild steel, that up to 20 millimeter, that one kind of stress pattern, and up over 20 millimeter diameter we are having another one. And I have already told that in the last class. So, this is your that section, we are talking say rectangular section, we can say that T section also possible, L section, inverted L section also possible, that we shall do it, but mainly we shall do it in the limit state of method, because that is the method which we shall consider and which we shall use it. So, we are getting that one say width B, depth, overall depth capital D, effective depth small d, and area of steel, that AST means area of steel in the tensile reinforcement, and this is the strain diagram, and this one you see, that one we are getting at this level, not at the bottom. We can get at the bottom also, but we are not interested. We are interested up to the steel bar level, and this is your that neutral axis position from the top, that x, and which we specify x equal to KD. So, this is one factor K which is important, and Z equal to JD, which you shall get it, that one you would say lever arm. This is your lever arm. This is the one compressive force at the CG of this triangle where it is acting. So, C, and tensile force T in the steel bar, and you will get the lever arm Z, which is again specified as a Z equal to JD, and we know that J equal to nothing but 1 minus K by 3. M equal to 280 by 3 sigma CBC, that we have to calculate the modular ratio. Instead of calculating from ES by EC, we shall calculate it from M equal to 280 by 3 sigma CBC. We shall calculate that from the bending stress in compression of that concrete. From there we shall calculate, because we do not know what is the value of PC, it is difficult to get, but it is easier to get sigma CBC also, because we can get the characteristic strength, then we can do the required factor, and then we can get the sigma CBC. And C equal to and C, that force in the concrete part, that in compression. So, we have already given half FCB B into X, T equal to FST AST. M could be calculated on the basis of CZ, compressive force multiplied by the lever arm. We can calculate the moment of resistance M, or we can calculate on the basis of T. And in fact, we do it, we calculate it, that whenever a concrete section is given, that we shall solve one problem today. Whenever a concrete section is given, then we have to find out the moment of resistance, and that moment of resistance we have to find out. We have to calculate moment of resistance due to concrete failure, that if concrete fails, and we have to calculate the moment of resistance if steel fails. And out of these two, which one will be the minimum, that we have to take, because it can fail before the other one reaches the failure. So, that is the standard procedure, we have to do it, and I shall show you one problem today for that, how to calculate moment of resistance. Before going to the calculations, let me tell you that what is balanced sections. Balanced section, it means a reinforced concrete section is called a balanced section when the maximum allowable stresses, that means sigma CBC in concrete and sigma ST in steel. So, when the maximum allowable stresses in concrete and steel are reached simultaneously. So, obviously, we can say that is the one optimum section. If we can reach, say, in steel as well as in concrete same time, then only we can say that we have designed an optimum section, and truly speaking it is not possible. We cannot provide a section which is, but we can come closer, but generally we have to do that closer, but we cannot exactly, we cannot make it. If you have to make it, then your depth of the section, it will be irregular, the number will not be, say, some regular number. So, number could be something, say, fractional. So, that is not a good choice, because if we go for that one, if we would like to optimize in that aspect, the other aspect is that formwork, shuttering, that one also it takes a lot of that cost, that it costs much. So, that one also you have to take care, and you have to use the formwork repeatedly. It is not like that for each and every beam or column you will use different formwork. You have to do it such a way so that you can reuse your formwork, then only you can optimize your cost also. So, that is another aspect. So, our strength criteria definitely one aspect, but we have to consider other aspect also, other practical difficulty also. So, that is why we compromise with certain kind of strength. Okay, if we can reach within 10% or 15%, okay, that means it is an optimum design, that we can say. Next one we call it that under reinforced section. So, that means that when the section is not balanced. So, when the section is not balanced, we mean to say that it is also possible that related to steel, I can say that reinforcement steel, either that could be less or that could be more. because balanced is something that which is equal to the concrete strength. Now, when we are talking say steel only, so steel area could be more or could be less, because we have only two other options. So, if it is say more, that is we call it one part. If it is less, then we call it under reinforced section. So, the under reinforced section, it means the sections in which the steel provided is less than that necessary for the balanced section are called under reinforced section. So, this is the section where we are having the reinforcement less than the balanced one. It means that concrete will not fail first, steel will fail first, and that one we require also particularly for say, that means when you are having say steel, it will fail first. It means that you are giving certain time for failure, because steel, it is a ductile material, it will give you some time for deformation. So, the occupants of that particular building will get some time to get away from that particular room, particularly for say earthquake. If you would like to design earthquake resistant structure, so it should be better that we should use under reinforced section, and also if we can use mild steel which is more ductile, so we shall get, you will get some time to get away. But generally of course, it is not possible nowadays to extensively use the mild steel, but the section at least it should be under reinforced.
Why is it not possible to use mild steel?
Because mild steel, okay, we shall come to the next, we shall find out, because strength of mild steel is different than strength of say your high deformed that HYSD bar. So, obviously you need more steel, and that is why we prefer that say we go for HYSD bar. So, the other one is called over reinforced sections, sections in which the steel provided is more than the balanced sections are called over reinforced sections. So, we shall consider this one as say over reinforced sections and under reinforced section. So, now let us see the balanced sections. Because we can find out the steel also. Let me just, I think I can go back to the few previous slides that, yes. So, this is the one we are interested. So, x and this one d minus x, this is x and this is d minus x. So, now let us find out that or we can write down here also, at least for this page. We are talking this one x and this part effective depth d minus x. So, we can write down FCB at the top So, we can write down KD x equal to KD. So, that I am writing here, and MFCB by FST. So, we can write down K equal to, let me make it, you please check it, because we are not going to detail of that calculation. and j equal to 1 minus k by 3. So, for the balance section we can find out k, that kd. So, that means if we know FCB, FST and FCB and m obviously we can find out m equal to 280 by 3 sigma CBC. We should remember this one. And FCB means sigma CBC and FST sigma ST. So, for a particular grade of concrete and for a particular grade of steel, what we can do, we can find out that value of K, and if we know K, then we can find out J also, and if we can find out J, then we can find out that JD, then we can find out moment of resistance, all those things we can calculate. So, here that FCB, FST, that one you are limiting permissible values, and that one we shall get it from code, because our code gives that permissible stresses for a particular grade of steel, for a particular grade of concrete. So, we can go, let us see. So, we can go here, let us write down FCB equal to sigma CBC, and just make it here for M15, M20, M25, M30, 5.0, 7.0, 8.5, 10.0. So, these are permissible stresses for different grades of concrete. FST for balance section, it should be sigma ST. Let me complete this one with giving the proper unit, and this one also Newton per square millimeter. So, for FE 250, FE 415, we have 140, we have 230. There is one more grade, that is FE 500. There is one more grade, that is FE 500, and that also we can use it, but I am giving only those because you can get those things in your code. So, in this particular class, if we cover all the each and every numerical values, then it will be difficult to cover all those things. So, we are only using those grade of concrete and steel which we generally use, and others, say FE 500, you can get it in IS code. So, IS 456, that also you can find out, and there you can get in detail. So, K equal to M sigma CBC divided by sigma ST plus M sigma CBC. I repeat once more, M equal to 280 by 3 sigma CBC and K equal to, please note there is one more K will come, that is capital K. So, but this one for the timing we are only working on, say, small k, that KD. So, that one comes as and J equal to 1 minus K by 3 and capital K equal to Kj by 2 and moment of resistance M, that one will be equal to capital K sigma CBC B d square. So, m equal to capital K sigma CBC B d square. This K, that is one factor. If you remember, for homogeneous rectangular section, in the last lecture we have found that is 0.167 times the stress times B d square. So, here also this capital K also we shall get similar type of one fraction that we shall get. So, let me go a little bit faster here. Okay. So, we can find out that beam factors for Fe 250, we can find out beam factors for Fe 250, that K we can find out for different grades of concrete. K you can find out that all of them having same, because for Fe 250 you please note this is your that equation. So, in this equation you will find out it is independent of sigma CBC, it is independent of any concrete value. We are getting only sigma ST. So, that is why you will get for any grade of concrete you will get that K same, and you can calculate J, you can calculate capital K. So, if we come back to this beam factors table, the small k, which is the factor of KD, from where you can get that say 0.4 times small d, that effective depth. So, we shall get the X, J which will give me the lever arm, and capital K, that coefficient you can get 0.174. So, all of them we are getting 0.174, and this one for mild steel. So, this table for mild steel for Fe 250, and I have given only M15, M20, M25, 30 just to show that for all grades of concrete we are giving the same value. Next one, that is for Fe 415. Fe 415 we are getting that K 0.29, J 0.9, capital K 0.131. So, this value you will get it say 0.167, the one we have told that one, and where here you are getting 0.131, the other one you are getting 0.174. So, that means you can approximately that is not a bad choice, one can also get some kind of result even if you get say homogeneous, but that is not, obviously it is not a correct one. So, the correct one what we are doing now. The next one I shall tell you. So, I can go a little further. The balanced steel percentages. So, if we say PT or P, whatever we consider, P equal to say 100 AST by BD. This is the percentage of steel what we are considering, and so AST equal to so we can equate forces half sigma CBC times KD times B. This is the compressive force, B times X. This is the compressive force B times X that we are talking. So, this is the one we are talking, this force C, and this is sigma CBC, this one X. Width of the beam that is B. So, I can get capital C half sigma CBC KdB, x is nothing but Kd. That we can get it, which should be equal to P by 100, we are talking percentage of steel, P by 100 BD times sigma ST. So, this is the area of the steel times sigma ST will give me the tensile one, the other one this one, this is the tensile force T. So, from here what we can get, P will be equal to 50 K times sigma CBC by sigma ST. If we just multiply, just rearrange it. So, P percentage of steel will be equal to 50 times K sigma CBC by sigma ST. I know that K, so I can calculate that balanced percentage of steel. So, I can get the balanced percentage, because this one required sometimes that you can approximately you can find out also, considering the sigma CBC by sigma CBC and sigma ST, you can find out K, and then you can immediately you can find out that P also, that you can find out. So, percentage of tensile reinforcement for balanced section, and we can get the grade of concrete, again we have taken 4 grades only, and sigma CBC just to give the value, and this is your that Fe 250, 140 and 230 we have considered. So, this is your that balanced percentage of steel. So, for M15, that means sigma CBC and sigma ST, so 0.71, we can get for the corresponding 0.31, here it is 1, 0.44, 1.21 percentage, where it is 0.53%, almost say even less than 50% you can say. The torch steel you need less than 50%. So, you can find out that you require less than 50%, obviously that we can, that is why we go for the torch steel, and we can find out that say even it is less than 0.63, it is 1.43. So, this is your that percentage of tensile reinforcement for balanced section. I shall come to the next point. We can find out that analysis one we call it design, another one we call it analysis. Analysis means that when the section is given, reinforcement and the depth, width, everything given, then we call it analysis. Then we are analyzing that how much load it can take, what is the moment of resistance, and design means that your moment is given and you have to provide the suitable section, and that is called design. So, here we are doing the analysis. So, analysis of a given section, and we are talking bending only. So, we can do it, we can take the moment about the neutral axis, so this one we are taking, so what we are doing, we are considering say neutral axis somewhere here. This part is Kd, area of steel somewhere here. area of steel somewhere here, and that distance d minus kd. So, this area of steel, so we can get the area B times kd by 2. I am taking the area with respect to the moment of this area with respect to this neutral axis, and moment of this area, because we are considering that equivalent section. That is why you have multiplied, this is the area of steel, P by P is the percent of steel, P by 100 times BD, because we are considering that one always percent of steel with respect to the width and times the effective depth. Please note width times effective depth, not the overall depth, because there is one more term, that is capital D, which is called overall depth, but we are not considering overall depth. So, whenever we shall consider the percentage of steel of a particular section, then we shall take it B times D. So, B times D multiplied by P by 100 will give me the area of steel, multiplied by M is giving me the corresponding, say, equivalent concrete section, that is the for any composite, say wood or say I think you have done it in first year class, wood and your say steel bar. So, that either you have to make that steel bar, you have to make it say the equivalent say wood area, or wood you have to consider it as a steel. So, wood will become thinner, but if you make say steel, convert it to wood, then it will be bigger. So, here we are considering the same way and multiplied by d times 1 minus k, that is the distance, and we shall get this equation. From there we can find out k square and in the last class also we have done it, and k equal to last class we have told that is a reinforcement index, and here we are talking say percentage of steel, and where P equal to so we can write down P 100 AST by BD, and from there we can find out the corresponding K. That K we can calculate, if area of steel given, then we can calculate that K. So, we can just repeat moment of resistance. Let me write down moment of resistance M equal to P by 100 B D sigma ST D 1 minus K by 3. Also we can write down in this way M by BD square equal to P by 100 multiplied by 1 minus K by 3 sigma ST. So, generally in SP16 for in any design aid, or you can make your own also, that we can use this equation which is independent of B and D. We can get a curve or we can make a table knowing that giving say P and for a particular grade of steel, we can find out, and for different percentage of steel we can find out that corresponding M by BD square. And then also we can do it, that means we can make those things ready and we can immediately, it will be faster in your design process, because every time you need not do to either calculator or computer, you need not do it. So, what you can do it in this way, you can make that curves or tabular form, and immediately you can choose that your section. Okay. Now, let us do say one problem. I hope we shall be able to finish it. Let us describe the problem first. Singly reinforced. Please note, I have already mentioned one term, singly reinforced, that means single. So, that means there is a term should be something else, generally we have double. So, that we shall tell afterwards. So, we are having one beam width B 250 millimeter, overall depth 400 millimeter. Let us put it as capital D. This is capital D. Clear cover we shall consider say CC 25 millimeter. Reinforcement phi. We designate phi, which if we specify phi, that means we are considering mild steel. Okay, there is one more actually there, that I shall tell you in due course. And Fe 250 and M20 grade of concrete. So, this is the description of the problem. This is 250, overall depth 400. There are 5 bars. There are 5 bars, 525. So, this is your that problem, we have to solve it. Okay. So, sigma Fe 250 phi 20 millimeter, sigma St, it is up to 20 millimeter. So, we have to use 140 Newton per square millimeter, not 130 Newton per square millimeter. M20 sigma CBC So, always you should write down first the values whatever you require, and M equal to so we know M, sigma St, sigma CBC. Okay. So, shall I continue with the next step? I think I can change it. bx square by 2 d equal to 400 minus 25 is the clear cover, 20 by 2, which comes as 365 millimeter. So, 250 m is 13.33. Area of steel, let us calculate here. Five pi by 4 to 20 square equal to, so 5, I think, so 1570 square millimeter. Or x square plus 1570 divided by 125 times x minus so I think I have to calculate it, divided by 125. Okay, or x square plus which is coming as 167.42 x minus 13.33 into 1570 into 365 divided by 125, which is coming as 61110, say that is equal to. So, x equal to plus minus divided by 2. Okay. So, which comes as let us little bit elaborate. And 167.42 into 6 so 260 or let us say 261. So, x will become 261 minus 83.71. So, 177.29 millimeter. Okay. So, we can write down M1 number 2 due to concrete failure, sigma CBC equal to 7.0 Newton per square millimeter. M1 equal to B x sigma CBC by 2 d minus x by 3 equal to 250 177.29 times 7 by 2 365 minus 177.29 by 3 equal to 5 minus 177.29 by 3 . So, 305.9 into 7 by 2 into 250 into 177.29. So, which comes as 47454402 Newton millimeter, which comes as 47.45 kilonewton meter. We get 47.45 kilonewton meter. That is due to concrete failure. So, we have to get the other one. So, we can get it the other one. So, M2 due to steel failure. Here sigma ST equal to 140 Newton per square millimeter. M2 equal to AST multiplied by sigma ST multiplied by lever arm. AST equal to 1570 millimeter. M2 equal to 1570 multiplied by 140 by 365 minus what was the lever arm, that 177.29 by 3, which comes as 'So, we are getting 67237553 Newton millimeter equal to 67.23 kilonewton meter. We have got M1 due to concrete flake 47.45, and here we are getting due to steel 67.23. That means moment of resistance M will be equal to 47.45 kilonewton meter. It will be governed by that you say concrete. It is that means it is over reinforced section. So if we go, that means concrete, and that is not a desired choice. So that means you can reduce your reinforcement. You can reduce your reinforcement, and you can find out that your optimum section. Yes.
Is it like there is use for under reinforced structures in earthquake? Is it used for over reinforced structures also?
No, we generally avoid that over reinforced, because that one also not economic also the other way, because if the concrete fails fast, that means that is not economic also. I don't know whether I have nothing. So we shall conclude with the working stress method, just to give an idea, and we shall compare with the limit state method also, but mainly now on we shall work on limit state method. So in the next class we shall start limit state method. Okay, thank you.